The most valuable bare rock. LHS 3844b has zero atmosphere, and this non-detection is a superior engineering result to finding a dozen gas giants. While the marketing around Webb usually highlights the search for biosignatures, this bare rock provides the first hard mineralogical baseline for an extrasolar crust. We finally have a geological zero for terrestrial worlds orbiting M-dwarfs. The data from the mid-infrared instrument provides the cold reality. Engineering the spectroscopic null. Detecting nothing is a technical triumph. In the May 2026 data release, astronomers used the mid-infrared instrument to measure the thermal emission of LHS 3844b as it passed behind its star. By comparing the planet-to-star flux ratio across 5 to 12 micrometers, the team achieved a signal-to-noise ratio that definitively ruled out even a thin, Mars-like atmosphere. If carbon dioxide or water vapor were present, the thermal inertia of the day side would have dropped significantly. Instead, we measured a blistering 1000 Kelvin peak, indicating total solar absorption by raw planetary surface. These mineral signatures suggest a world of dark, volcanic rock. The basaltic floor. The spectrum perfectly matches basalt. This is a specific signature of iron and magnesium-rich lava that solidified without the interference of standing water. This finding eliminates the possibility of an Earth-like granite crust, which requires plate tectonics and hydration to form. But the missing volcanic gases point to a deeper problem with its host star. The M-Dwarf Filter. The absence of sulfur dioxide is the critical constraint. On an active volcanic world like Earth or Io, geological outgassing would replenish at least a tenuous envelope of gas. On LHS 3844b, Webb found absolutely nothing. This suggests the red dwarf star's high-energy radiation and stellar winds are so aggressive that they strip away secondary atmospheres faster than the planet's interior can produce them. We are looking at a permanent erosion state, where the star effectively sandblasts the planetary surface into a fine powder of iron-rich regolith. This is a hardware-level restriction for any planet orbiting a small, active M-dwarf at this proximity. This non-detection changes how we prioritize future observations for the TRAPPIST-1 system, the triage of terrestrial worlds. This definitive non-detection on LHS 3844b transforms the search for Earth-like planets from a survey of hope into a rigorous process of elimination. By linking the basaltic composition from the earlier mineral data to the atmosphere stripping caused by stellar winds, we now have an empirical boundary for the M-dwarf habitable zone. This data suggests that the mission profile for finding biosignatures around red dwarfs needs a complete overhaul, shifting focus toward planets with significantly wider orbits or more robust magnetic protection. For system designers and mission planners, the era of hunting for any rocky planet is over. The focus has shifted to the specific orbital and magnetic constraints that allow a crust to actually hold onto its air. Watch for the TRAPPIST-1e mineralogical survey, scheduled for late 2026, to see if this bare rock trend is universal. Subscribe for more.